Now that we have a good sense of the three-dimensional shape of molecules, we're going to look at the role polar bonds play in determining whether or not a molecule is overall polar. And so we've talked a little bit about polar bonds in terms of differences in electronegativity. And then if you have more than one type of bond within a molecule or a compound, then we're going to have to look at the shape of that molecule to see whether or not the molecule overall is polar. So starting with the polar bonds, we have carbon-oxygen bonds in both of these compounds, carbon monoxide and carbon dioxide. And to determine whether the CO bond is polar or nonpolar, we need electronegativities. Well, carbon has an electronegativity of 2.6, oxygen is 3.4, the difference is 0.8. And we know that the difference between 0.4 and 2.0 means that we have a polar molecule. So what we want to do on these molecules is label the dipoles, or where's the positive and negative within this unequal distribution of electrons. So the carbon is more electronegative, the oxygen is more electronegative, takes the negative charge, or the partial negative, and the carbon is going to take the partial positive. Same thing in the CO2. We're going to dump that partial positive on the carbon and partial negatives on each of the oxygens. And so when we look at the molecule on the left, the carbon monoxide, there's a clear separation between positive and negative. But on the right, we have two negative charges. And really, if you want to figure out whether or not there's a separation of charge, you need to reduce all of your charges to a single positive and negative. And we're going to do that by finding the center of charge. Well, the center of the positive charge is obviously on the carbon because there's only one. But if we want to look at the center of the negative charge, it's going to be the halfway point between where those two negatives are. And it turns out the center of the negative charge is in the same spot as the positive. And so what you're going to have there is a cancellation of those polar bonds to reach an overall nonpolar molecule. So you have a polar CO, but a nonpolar CO2, even though both of them contain polar bonds. Another way to think about this is in terms of, can you generate a charge separation by drawing a line somewhere on this molecule, keeping in mind three-dimensional shape. Now, these are both linear molecules, so it's pretty easy to represent them in two-dimensional space. And if we draw the dotted line there on the carbon monoxide, there's a clear separation with positive on one side and negative on the other. It's much more difficult to find a line that puts all the positive on one side and all the negative on the other because you have those negative poles on either end. And so because you cannot create that charge separation, we consider that molecule to be nonpolar. Let's look at this in terms of our molecules which have tetrahedral electron domains. So these are three molecules that we looked at when we first introduced this idea of molecular shape. And so let's start with the CH4. The electronegativity of carbon is 2.6. Hydrogen is 2.2, and of course we know that carbon-hydrogen bond is kind of our definition of nonpolar. And so if all of the bonds in your compound are nonpolar, you get off pretty easy from an interpretation standpoint because then the molecule has to be nonpolar. Let's go over to the NH3. So the hydrogen has a 2.2. Nitrogen's electronegativity is 3.0. So now we're at 0.8 and we have a polar molecule. So let's go ahead and label our dipoles. We're there and there. Negatives on the nitrogen, positives on the hydrogen based on electronegativity. And so because this is three-dimensionally in the pyramidal shape, I can draw that line that separates the top of the pyramid from the bottom of the pyramid, and we have a clear separation of charge. If we're thinking about this in terms of center of charge, think about, again, this pyramidal shape. The negative charge is on the point, whereas the positive charge is going to be at the center of the base. And so, again, there's a clear separation here between positive and negative. And so we're going to get that polar molecule on the NH3. All right, let's look at the H2O. We have a 2.2 on the hydrogen and a 3.4 on the oxygen. The difference is greater than 0.4, so we know we have a polar bond. Let's label our dipoles. And then let's look for the center of charge. Well, where would the center of charge be? In between the hydrogens. And sure enough, we can draw a separation between the center of the positive and the negative charge. And so we know there we have a polar molecule. Another thing to think about in terms of molecule polarity is symmetry. A molecule that has polar bonds but also is symmetric will tend to produce a nonpolar molecule, where something that contains polar bonds and asymmetry is likely to produce a polar molecule. So looking at this CCl4, we have 2.6 electronegativity on the carbon and 3.2 on the chlorine. The difference there means we have polar bonds. So if we go about labeling our dipoles, we get this situation here. And there's no way to draw a line that puts all the negatives on one side and all the positives on the other. In a sense, you have chlorines pulling electrons in 4 equal and opposite directions, and so you get no net movement of electrons. And so you can't create the imbalance, which creates a polar molecule, so this would be nonpolar. But let's just take one of those chlorines and replace it with a hydrogen. Now we have a nonpolar bond between the carbon and the hydrogen, so we won't label that one. And now that we have this asymmetry, we can go back to our rule on charge separation, and I can draw you a line that completely separates the positive charge from the negative charge. Again, essentially, you got a hydrogen sticking out the top of a pyramid here in terms of where the polar bonds are. And again, that S plus, or that delta plus, is on the point of the pyramid. Center of the negative charge is going to be between the chlorines but below the carbon. And so you end up with a polar bond there. And that is a pretty good overview of bond polarity or molecule polarity.